recording. Good morning, everyone, and welcome back to the first session, which is about innovative approaches to PFAS management. Our first speaker is going to be Dr. Bani, and Dr. Bani is going to speak to us about the tailored approach, multi-stage remediation to address PFAS challenges at a commercial airport. Now, he's not in person, he's going to be remote, so we're going to have him up on the screen. So, Dr. Bani?
Thank you so much, Justin. Good morning, everyone. As Jason mentioned, I'm going to be talking about the multi-stage remediation to address PFAS challenges at the commercial airport sites. This is a project that I've been working on since 2021. I would go off camera just to save bandwidth, but I'm going to be on camera again during QA. For agenda for today, I'm going to be talking about the project background, the remedial approach consideration, followed up by the program overview, some of the investigation that has completed so far on site, hotspot remedial actions that was taken, as well as the conclusion. For project background, this is an active airport site, commercial airport site in Canada. The current owner of the site is the city, the local municipality, but this site has been previously owned by the federal government when previously firefighting training activities had taken place using a FFF known to contain PFAS. Because the federal government was responsible for those activities at the time, when they own the sites, the city has come into agreement with the federal government for the costs and provide funding for remediation and management of PFAS at the airport. So there is a shared contribution agreement currently between the city and the federal government, and this contribution has the expiry date, so the timing is an essence, as well as the funding, the total funding available to the city to manage PFAS at the airports. At the down gradient of the airport sites, there are existing residents that their drinking water wells have been impacted because of the PFAS activities previously at the airports by the federal government, and there are existing drinking water mitigation measures in place by providing bottled water to the residents, as well as advisory levels for fish advisory levels for fish consumption in the area. The city has hired Jacobs to support the airport PFAS remediation with the objective of reducing risk to human health and the environment associated with on-site PFAS contamination. So when we wanted to look at the remedial approach, we wanted to consider a couple of things, and which was important to this project. The first one was the timing. This contribution agreement has an expiry date. So it was started as a 3-year contribution agreement, then it extended to 5 years. So you have to come up with a remediation program that matches those expiries and meet those goals within those expiry dates. It also comes with the available funding, so it also needs to match the funding agreement. The remedy must be implemented by that expiry, and we also need to consider all the permits and approval before the construction starts to meet those timing requirements. There are some site-specific conditions that we need to consider. The risk driver was the groundwater used as offsite drinking water source. As I mentioned, the driver was to minimize the offsite contaminants migrations. There is also soil contribution to the groundwater through leaching, and the goal was to limit that soil volume that exceed the risk-based goal at the site. There were other on-site sources of PFAS, the runway, the concrete pads, as well as site infrastructure in terms of the surface water and drainage ditches at sites.
Dr. Bani.
Yes.
I apologize. we lost you a couple minutes ago, and I hate to tell you this. It was right after that first slide. And I'd hate for our audience to miss what you've been speaking about. Could you go back to that first slide? I apologize. It just, there you go, right there. When you got about a couple minutes into that, or a couple words into that slide, we lost it.
All right, so
Internet connectivity.
sure.
Thank you.
Let me know if you can hear me now.
We can hear you now.
All right, thank you. All right, so um, I can start that from the beginning. Let's so this is a site, the airport site that is now currently owned by the city, by the local municipality, but it has been previously owned by the federal government of Canada. And very previously, firefighting training activities had taken place. And because the federal government by using AFFF at the time, which was known to contain PFAS, was responsible for those activities. There is a shared contribution agreement between the city and the federal government, so that the federal government provides funding for any remediation and management of PFAS at the site. Down gradient of the site, the residents uses the drinking water wells. So those drinking water wells has also been impacted by those previous activities at the site. And there is existing program in place for providing bottled water to the residents, as well as fish advisory level for fish consumption in the area. The city hired Jacobs to support the remediation project, and with the objective of reducing risk to human health and the environment associated with on-site PFAS contamination. So when we wanted to start the remedial approach and considering those remedial approach, there are a couple of considerations that we had to take into account. The first one was timing, and that was important because that contribution agreement with the city and the federal government had the expiry dates. So we had to work within that contribution agreement time frame. And it started from 3 years, then it expanded it into 5. But we had the set goals and set timeline to meet, and as well as the funding, available funding as a part of that contribution agreement. The other conditions and consideration was site-specific conditions. So the risk driver for the site was the groundwater, which is used as an offsite drinking water source, and the driver was to minimize those offsite contaminant migration, soil contribution to the groundwater through leaching, and the goal was to limit soil volume that exceeds risk-based goals, as well as other on-site sources, and that includes runways, the concrete pads, the site infrastructure as drainage ditches, for example, on site. The other consideration that we had to, in terms of the site-specific condition, was bedrock. So the site has uh, granite bedrock um, that has been impacted by PFAS. So even very deep 100 feet into the bedrock, the concentration of PFAS was found, and the goal was to minimize that offsite contaminant migration through those bedrock pathways. The stakeholder was also very important as a part of our remedial approach, and that's to manage competing interests and concerns from various stakeholders involved on the projects. And with the overall goal of minimizing the risk, financial, compliance, and exposure risk to the clients. So on this, stakeholders and on managing competing interests and concerns, this is very it was a very important part of our remedial approach, and I want to touch base a little bit more on that. So if you want to look at, there are 6 major stakeholders involved on this project, and from the city, from the airport operators, the federal government, the local regulators, and the local district health unit and community itself. And we wanted to, every single stakeholder has their own interest, and the goal is to focus on common goals from these stakeholders. And looking at the city, for example, they're looking to maintain active airports through the operation, managing long-term risk, but they're also looking at low cost, risk reduction, quick implementation, and looking at the regulatory bodies and the federal government, and we looking and try to make those common goals. You're still looking at the low cost, risk reduction, quick implementation as a part of the common goals. And for that, the overall objective of the project was designed, and that's to develop achievable and cost-effective solution to meet those project-specific objectives in a shortest reasonable time frame. So with that in mind, we started looking at the developing a program for the PFAS management. And again, going back to that contribution agreement, we had a 3-year window, 3 to 5 year window to meet those objectives and goals. So we started defining the PFAS problems at the site. And that starts with doing a PA and SI, similar to the circular process, and moving into the evaluation stage by doing site-specific risk assessment, RA, doing some additional field sampling, which is similar to SI and RI for additional investigation for site investigation and remedial investigation program, as well as doing some triviality studies to evaluate options. Then it goes into management steps where we look at the risk management measures, some active site remediation program to manage the highest impacted zones, and provides remedial action plans and actions, as which looking at the pilot testing to support some of those decisions. And the other thing was that I didn't touch at the first slide, but the downgrading of site, when I mentioned the residents are also impacted, the source of the drinking water to the municipality, to the city, drinking water has also been impacted as from the works that from the previous firefighting activities taking place at the airport site, and that also was a consideration for the project to see the work that we are going to be doing at the airport site, has that going to impact that water treatment plants, down gradients, and the sources, and do you need to upgrade that to also remove PFAS at the plant itself? So the first step I mentioned was to evaluate and do evaluate PFAS sources, field sampling program. As a part of that, in 2022 to 2023, we completed a very comprehensive field sampling program to look at all soil, groundwater, surface water, and sediments at the site. And we completed 186 soil samples, 138 groundwater samples, 120 surface water samples, 38 sediment samples. And with all of the sampling we've done, the goal was to identify the locations, because again, we had the limited funding available as a part of the agreement with the time frame that we had to meet those remedial goals. So the idea was to prioritize the areas on site that we can remove as much as possible of PFAS mass from the site, so that we can meet the goals and objective of those contribution agreement between the city and the federal government. So the next step we have taken was a site-specific risk assessment. We completed a typical approach for PFAS with 8 of the PFAS which does have TRVs values, but we also look at we did the new approach methods, NAMs, for other PFAS. So utilizing some of those 8 PFAS with the TRVs, using the NAMs, we did it as site-specific risk assessment, which was submitted to the regulators in spring 2024. As a part of that, we identify in terms of the health risk, there are potential and acceptable risks associated with the worker ingestion of the groundwater and the surface water, sediment and the sediment contact for for workers, and soil leaching to the groundwater as a main risk drivers for the health and for the eco risk. We did not find any unacceptable risk at the site in terms of eco risk for the site. So the next step was, and this is a part of the regulators was very interested to identify if there are any precursors, and not only known PFAS as PFOS for PFOA, for example, as a in the water, in the groundwater, in the soil. To answer some of those questions, we developed a very comprehensive, detailed assessment, very comprehensive framework to complete a detailed PFAS precursors assessment. We look at the preliminary assessment by looking at doing a top assay on 68 samples, 122 samples, and 122 samples, routine 1633 samples for that assessment alone, including 68 of topo samples. And we look at those as a preliminary assessment by looking at the difference between the top and pre-top samples. We look at the detailed assessment based on the top assay chemistry. We identify the acceptable range. We develop those range based on the differences between the top assay results for the pre-oxidation and post-oxidation, for example, with the different precursors from different type of PFAS identified in terms of the carbon rings identified at the site. And we did that for both liquid soil and liquid samples and soil samples, and we identified the methodology to assess the presence of those PFAS precursors. Overall, what we have found as a part of this assessment is there was no significant evidence for precursors found at the site. So, and mostly PFOS was the primary PFAS identified at the site. So in terms of for what we have done so far at the time, we have found that PFOS was the predominant and analyzed reported for all media type. And that was consistent with the type of AFFF, 3M light AFFF that was used at the time of when those firefighting training activities was taking place. The soil contamination above the regulatory screening criteria was also limited only to the top 2 meters at the sites. The groundwater contamination was found to be site-wide. So there are groundwater contamination above the drinking water criteria. The challenge we had for this project overall was, and it's in many cases it's maybe it's a global challenge, is the PFAS regulations are evolving rapidly, and for that, even within our investigation and as a part of this program, in between our investigation, the criteria, drinking water criteria in Canada has changed, in Ontario has changed from 70 nanogram per liter now to more of the federal drinking water criteria of 30 nanogram per liter. So we had to adjust our approach and the investigation program to have to adapt to these new goals. The three settings that was most interest to us as a part of the groundwater remedy approach and for the contamination for the CSM was looking at the overburden, which mostly consisting of sand and gravel at sites, but also looking at the shallow bedrock as well as the deep bedrock at site, because we understand that, yes, so both shallow and deep, we had concentration of PFAS found in those two units. However, managing the PFAS at very deep bedrock in a granite bedrock is not considered as a practical tools to meet those project objectives within the time frame and the funding agreement that is in place. So we have to develop the priorities. We have to develop what can we do, and as a part of it, we wanted to use the tools available to us to maximize the mass removal um, by maximizing and optimizing that remedy within those specific units. The surface water contamination has also been found at various locations at site above drinking water criteria. I'm not going to talk today. I'm not going to talk about the surface water. We are now in the process of doing a pilot testing for this year. But one thing that I want to emphasize is based on all of the works that we have done, we have identified the highest concentration with in both soil and the groundwater was associated with the firefighting training areas. And that's where we wanted to make sure that we focus our funding, available funding with the resources to maximize that mass removals within those hot zones area. To support some of those decision making, we started doing turbidity testing, and we did the turbidity testing for water, for soil, looking at the rapid small scale column test for water to identify the absorption, to evaluate different absorbent as a pump and treat system, for example, for groundwater, as well as for injection of the materials into the aquifer by looking at the permeable absorptive barrier column testing done for two different colloidal activated carbon and one specialized sorbent. We also, for soil, we also look at the soil stabilization as a potential remedy option and soil washing and recycling. For soil stabilization, we look at 3 commercially available products as a part of that turbidity testing. So now that we have evaluated the option, we identify what can work with the site-specific site-specific soil and water testing. We identify the hot zone is in the FFTA areas. We define the remedial actions, and that is to manage those hotspots that can be maximize the amount of PFAS, the mass of PFAS that we can remove as a part of this project. So for firefighting training areas, we look at the excavation, offsite treatment, disposal of soil through the incinerations, the in situ soil mixing with PFAS specific sorbent at the bottom of the excavation. So 1/2 meter bottom of the excavation, we mix the soil, and that not only it helps with the soil remediation of soil, but also with the groundwater remediation within those hot zone areas, and the groundwater using the groundwater absorptive barriers at the FFTA site boundaries to manage the offsite migration of plume from the site. For the surface water is also, we looked at the absorptive barrier at the select exit location. Again, the focus was on the mass, where the mass is moving. And to do that, we started looking at the tools. So we wanted to identify what tools are available to us. And one of we have done the EVS modeling. We've done the groundwater fate and transfer model at the site, and the photo that you can see to the right that shows an output screen of the EVS model that was developed as a part of this, and the goal was to remove at least 80% of the PFOS mass in the soil, and not we knew that there are still masses of PFAS going to be left in soil, but that's kind of like we wanted to make sure that we have a practical solution to meet the contribution agreement funding and the timing with the expiry timing in mind to maximize the mass removal. And as a part of all of these approaches, the very important approach is to engage the stakeholders in these decision-making process, because that's how you kind of build your trust with the stakeholders, with the regulators, and identify what is best, how we can manage PFAS at these sites that within that available funding and time. So what this slide shows is the FFTA soil remediation, soil excavation approach that was taken last year. The construction and the excavation remediation has been almost completed. It potentially is going to be in a couple of weeks. It's going to be fully completed. The hotspot soil removal was to remove any PFAS exceeding 10 times of the guidelines of 0.1, 0.01 microgram per gram. The important part that I want to also highlight is as a part of when we started designing the excavation and the extent of the excavation, it is very important to fully delineate and doing an additional sampling program and sampling, soil sampling, test pitting, drilling, to fully delineate the extent of the excavation. Because during the excavation, you wouldn't have time to because there's no screening tools, quick screening tools available now currently in the market. There are some that are still in the prototype. There are some that the lab is now expediting the process for that. But it's still we are not still there to have a tool available to us that we can go and direct the excavation live on the excavation project and to manage maybe any areas that we're gonna find during excavation that we have missed as a part of the investigation process. So it's very important to complete those pre-excavation soil sampling to fully delineate that area. And again, I did mention the in situ soil mixing at the bottom of the excavation, 0.5 meter was also used. And we included all of these information into that EVS 3D model to reevaluate how much of the masses has been actually removed as a part of this program. And we completed confirmatory sampling as the excavation was completed. And again, those confirmatory sampling was fed into the EVS model, and we confirmed more than 80% of the mass has been removed as a part of this process. The next step was to look at the groundwater remediation. Now that we have removed the sources of the masses in the soil, in the FFTA zone, we look at the boundary to see how we can offset and offset the groundwater plume and stop and mitigate that migration of the groundwater plume to the offsite property downgrading of the site. With the goal of to evaluate distribution and accurate placement of the absorbent within the target treatment zone and assess PFAS concentration reduction, we developed a pilot testing program with the colloidal activated carbon injection at the sites.
Dr. Bani, this is Gene Jones. Sorry, this is Gene Jones. Wrap it up for us, please, sir.
Yep. So I have only one more slide after this. So we've done the pilot testing, low injection pressure maintained. We did the colorimetric testing. All of these shows that we had the very good distribution in both overburden and bedrock, with a 29 to 90% reduction in overburden and 29 to 58 for shallow bedrock. For conclusion, it's very important to have a dynamic decision-making framework, which is very essential because the regulation evolves. You want to adapt to those new needs, especially when you're dealing with a complex site conditions such as bedrock, for example. And it's important to establish priorities, and that's you have funding available and timing to consider. So it's important to consider a dynamic and data-driven approach using some of tools like EVS or any 3D modeling tools. Multi-stage remediation approach is also a key. And one of the key elements of success is to have active stakeholder engagement to build that trust. And finally, the end goal was to optimize PFAS site remediation while addressing those stakeholder concern and environmental risk. So with that, if anyone has any question, I'm happy to answer.
Question up here.
Thank you for the, excuse me, thank you for the presentation. It's a twofold question. Is a precursor assessment always part of the assessment stage? And what if the precursors turned out to be above certain levels? Say, for example, I'm just going to use an arbitrary number. Precursor was greater than 50%. Is it going to change your remedial action plans?
So it doesn't necessarily going to change the remedial action plans. It does change the type of treatments and remedies that will be selected as a part of it. So now as a part of that work, now we are looking at some of the absorptive absorbents, for example, is still gonna remove PFAS and like PFOS, for example, or some of these precursors. It's just not going to be as effective when you're dealing with, let's say, with a more shorter chain PFAS compounds. So it does impact it doesn't impact the overall approach. It does impact the selection of those remedies.
Thank you.
Okay, I'm gonna just ask if we can not take any more questions. I apologize. Just because we had those technical problems up front, we ran a little long. So I'm just gonna ask if we could go ahead and switch over. It's gonna take a moment because we're switching over from remote, but thank you, Dr. Bani. We appreciate your topic and we appreciate your time.
All right. Thanks.
So-
Thanks, everyone.
So while we're switching over, it's gonna take me just a couple minutes to switch over from being remote to being prepared for us up here. And getting the slide switch over, I'm gonna